Okay guys, sorry there's a little glitch there at the beginning of the video. Well, welcome cohort A to the lesson for today. And wow, I'm rhyming like a Dr. Seuss rhyme. All right, so we got a lot to talk about today, so I'm gonna sort of start over here. Okay, so first, let me introduce you to circuit diagram symbols that you're gonna have to memorize. So here you can see the various symbols that we use to draw electric circuits, okay, by hand. It's something every grade 9 student has to be able to do. And so I've asked people to memorize these 1, 2, 3, 4, 5, 6, 7, 8 symbols. And as you can see here, this is a meter for measuring current. That's why we use the A symbol for amps. This is a voltmeter for measuring volts. So V for volts makes sense. A light bulb looks like that, okay? A connection point is sometimes referred to as a junction, and I usually color this dot in. That's where two wires are connected, or there could be a fork in the road. So you can have 4 wires connected, you know, to a junction point like that, or even more, okay, depending on the junction. A resistor, okay, is a jagged line, okay? We've already covered junction, but a resistor is a jagged line. An on and off switch looks like that. A straight wire looks like this. A battery looks like that, except this is one cell of a battery. They can be joined together to make more than one cell, and we usually label the voltage, okay, at the same time. An AC power source looks like this guy here. And finally, a ground wire looks like that, although you're probably not going to see ground wires in the circuits that we're going to be using today, or for that matter, the circuits that you're ever going to have to draw. Okay, now there's a few rules for drawing the circuit diagrams. So number 1, you must use the correct symbol, which I've just shown you, okay, for the various elements in the circuit. Number 2, you use straight lines, draw with a ruler, preferably, okay? And here's the thing, there's no diagonal lines. They're either horizontal lines, whoops, horizontal lines, or vertical lines only. So just take note of that when we're drawing wires. There's no gaps or breaks between the lines. That would indicate an open circuit. Okay, and the diagram should be large, which means don't use this really tiny sort of style of drawing things. Okay, they should be large enough, okay, that they're easily read. All right, let's give a couple of examples. So here we have 2 lights. I'll color them in yellow. 2 lights and a switch. Okay, here, this is the switch connected together with a battery. Okay, so when you close the switch, the lights will turn on. We call this a series circuit because if you were an electron, there's their little electron, and you are traveling through the circuit, you would have to make your way through the wires, okay, like this, through the switch. The switch is open right now, but if you could go through the closed switch, back to the battery, okay? So you've got the electron making its way through everything. Series means one after the other, so the lights are connected along the same path, one after the other. And when we say series circuit, what we mean is that basically there's one path. Okay, and that's a series circuit. Now for a parallel circuit has more than one path. And here you can see, I'll shade in the junction spots. There's 2 junction points here, like a fork in the road. Okay, so if you were, let's say, an electron, I'll use blue actually. You're an electron and you're trying to make your way around here. When you get to this fork in the road, you have a decision to make. You could go that way. Sorry, my smartboard's a little bit out of alignment. You could go this way along that path, or you could go that way along this path. So you have a decision to make. Electrons don't actually make decisions. They just are governed by the forces of nature. Okay, so in this case, they will take whatever path that nature dictates for them. Some will take one path, the other ones will take another path. The path that has less resistance will get more flow. Okay, so and it's just because it's an easier path, so more electrons will naturally go there. Okay, and then they join back up together over here. Okay, and then they go back through the switch to the power source. So we call this a parallel circuit because there's two parallel paths. But what you need to just remember is that when you have more than one path, we call that a parallel circuit. Okay, so there you go. These examples of how you draw circuit diagrams. Notice how I drew the wires. Well, the wires are horizontal or vertical lines. The correct symbols are used for the batteries and the lights and so on. And there you go. So there's some examples of circuit diagrams. All right. Now, let's get to the lesson for today. It's Kirchoff's laws. Kirchoff's laws are rules for how voltage and current work in an electric circuit. So let's just take a look at some of these rules right now. There are two rules. One is called the current law. Okay, and in physics, when we say laws, we just mean that's just how it works. That's just how things are. So we're just describing to you something that always happens. Okay, so what is the current law? Well, what happens is this. Let's say you have a fork in the road. Oops. Go back to a black color. I'm gonna draw it over here in the margin. Let's say you had a fork in the road. So a junction point, and flowing into that junction point is some current. Let's say it's like 10 amps of current, okay, flowing into the junction point. Well, these are always one-way streets. So you can't have anything flowing the opposite way. So the only way this makes sense is if you could have two currents going out like this. Okay, well, I haven't drawn that very well. There. Now, let's say this current here was 3 amps. Well, then how much is this one? Okay, so I think instinctively you might get this. If 10 amps flow into a junction, so this point here is the junction point, how many amps will flow out of the junction? Well, picture it like cars in traffic, okay? Let's say 10 cars arrive at an intersection. 3 cars turn right at the intersection. How many went straight through? I think you will intuitively guess that the answer is 7 amps, okay? Now, we could change the question a little bit and make it a different type. I'm gonna erase this. Picture is from something else. Erase this. Let's say we have 2 one-way streets again. Actually, I'm going to draw it a little differently. Looks the same as before, but this time I'm going to have 3 amps here. Actually, I'll make it, just to make it different, I'll make 6 amps here. I'll make 8 amps there. And the question is, what's this one? See, the 6 and the 8 are now getting combined at our junction point, and they flow out. There always has to be one of them, at least one path that leads out of the junction. So in this case, it's the path that's on the right. That's got the unknown current. Well, 8 cars arrive at an intersection, plus another 6 are arriving from underneath. That makes a total of 14 cars. So how many had to exit the intersection? Well, it would have to be 14 amps, right? See, and if you get that intuitively, if you understand what I'm trying to tell you, then what you're saying is that the currents have to add up so that the current flowing into the junction must equal the current flowing out, okay? And that's exactly how the law is stated. So here, sometimes I think it's better to just draw the diagram, but I'll draw the diagram for the current law. Here, we'll say I1, I2, and I3. And what we're saying is that I3 equals I2 plus I1. Okay, what we're saying is that the current flowing in, so this is what's flowing out. And this one is what's flowing in. So the way you state this law in words is the current flowing into a junction must equal the current flowing out. Okay, and I'm just going to highlight some of that. The current flowing in equals the current flowing out, right? Okay, and that is how current works when you have a fork in the road. And it's very logical. So the current law is pretty straightforward. Okay, so now let's do the voltage law. Now the voltage law is, well, it's pretty straightforward also, but anyway, let me just write it down for you. So number 2, the voltage law. So voltage, the way voltage works, and I don't have a lot of room right here, so I'm just going to write it in like next to the title there. So let's say you have a battery. Batteries, okay, batteries are short sticks and long sticks. Like this, I'll have a light bulb, I'll have a resistor, and I will have a second light bulb. This is how I draw them. Okay, and what happens is, let's say we have 120 volts in our power source. Let's say the light bulb, this light bulb drops 30 volts. So that's how much energy it uses per charge. Let's say this one drops 50 volts. Okay, and my question for you is, what's this missing voltage down here? Well, here's the voltage rule. As the electrons go through this path that you see here, okay, and make their way back to the power source, they have to follow a rule that says that they have to lose any potential energy that they gain, okay? So they've gained 120 volts, like this 120 volts in the battery is a donation, okay? Let's pretend it's like money. So I give you some money, and I say, here's $120, and you are going to travel through these 3 stores, and the rule is you cannot come back to the bank to get more money until you've spent all the money that you have. You have to spend every last dollar. And so if I gave you 120, that means by the time you come back to the bank to get another 120, you have to have spent the first 120 that I have given you. And here are the stores where you spend your money, here, here, and here. So how much did you spend at the 3rd store? Well, you spent a total of $80 in the first 2 stores. So you have $40 left. And so you have to spend $40 there. So this missing voltage will equal 120 minus 50 minus 30, which is equal to 80 volts. Okay, and that is the voltage law. And the way it's worded in words is you write the sum of the voltage increases along a single path must equal the sum of the decreases. Okay, it must equal the sum of the decreases. So the key word here is the single path. Okay, so that's along a single path. So in this circuit that I've shown you as an example, there is only one path, okay? But you can have circuits that have more than one path, parallel circuits, but they will still follow that law. All right, so now that you've seen these 2 laws, you see how sort of simple it is. Can you use these laws to answer some questions? So let's do this. Erase that. So here's an example, okay? So we'll call this example here, we'll call it example A. All right, take a look at this. This is a parallel circuit. It has 3 parallel resistors. You can see them there. They are here, here, and here, okay? And the question is asking us to find the missing value of current, which is right there coming out of the battery. Okay, so I like to use the analogy of like going skiing sometimes, okay? So you get off your chairlift, and this battery here is your chairlift, okay? Now some people get off the chairlift, and what happens is they travel off the chairlift along this path, then they reach a fork in the road. Now there are 3 possible paths for them to take, okay? The red guys go this way, the blue guys go this way, like that, but then the orange guys go this way, okay? And then what'll happen is, here the blue ones will follow this path up to here like that. The red ones will take this path up to here like this. The orange ones will continue all the way up, and then they meet again at another junction. And then I'll use a rainbow color. The rainbow guys all together will exit, okay, and go return to the chairlift at the bottom of the hill. Okay, so now see if you could follow along here. What's the missing current? Well, we know that when we get to the junction point here, this junction, we know that the current coming out of the junction is 2 plus 1 plus 4, okay? So flowing out of that junction is 2 plus 1 plus 4 amps. Well, therefore, the current flowing into the junction would have to equal the sum of those 3 things, which is equal to 7 amps. And so this missing current over here, I0 they call it, must equal 7 amps, right there. See how easy that is, guys? You just got to figure out how many skiers, like in this case, there were 7 guys that got off this chairlift. 4 of the guys took path number 3 here. 1 of them took path number 2, and 2 of them took path number 1. But we know that there's a total of 7, and that's what had to have left our chairlift, right? Okay, how about this one? Well, we're on our ski hill again. We'll use the same analogy. We're on our ski hill again. And what you can think of these things of as drops, these 3 voltages, these are called drops. So like when you go up a chairlift, it gives you a rise, but when you ski down the hill, you drop down the hill, okay? So how high is the hill is the question. See, you're supposed to find the missing voltage in the chairlift, which is the battery. Can you find the missing voltage? Well, if I had a drop of 20 plus another drop of 18 plus another drop of 12, as I take my single path, okay, this is the path the electrons take or whatever through the circuit here, and then they get back to the power source. As I take that single path, my drops add up to 12 plus 18 plus 20. So that is equal to 50 volts. Well, that must be what the chairlift gave me. So therefore, this would equal 50 volts. Right there. Pretty straightforward, right? So that is, these, believe it or not, guys, I got these 2 problems from a grade 11 physics textbook, just to, give you some sense of the level of difficulty. Not that difficult, right? Okay, so now let's challenge you a little. Okay, and let's look at this problem. Now, this problem has elements of both of the laws in one problem. Okay, so let's see if you can figure this one out. Both laws together in one problem here. And I always tell students, start with the current. So let's do find any missing currents. first, because those are usually pretty easy to find. The current law is very straightforward. All right, so let me highlight for you where the currents are. We know this one's 4 amps, okay? I know this one is 3 amps. This one here, I3, is unknown, and this one down here, I4, is unknown. Okay, so let's start at the top of the picture and see if we can't fill in one of the blanks, I3, okay? So look at this junction here, that junction, okay? In that junction, I've got 4 amps coming out that are making their way this way, see? 4 amps. Now, flowing into that junction is 3 amps, like it says right there. So let's use the current law. What is I3 then? So I3 would equal, use black, I3 would equal 4 amps. I'll just use 4. Minus 3 is 1 amp. So we just figured out that this one is 1 amp. And why? Is because those 2 one-way streets that feed into the junction, there's 4 guys coming out. That means 4 guys have to be going in. And we know if we see 3 come in from the left, so 1 has to come in from the right, okay? All right, so that is the current value. Oh, we're missing 1. Okay, so let's find the missing current at the bottom here, I4. And let's think about that for a second. Okay, I know that 3 amps, I'm going to write a little path here. This orange path that I am tracing right here had 3 amps on it. That means 3 amps had to come in from the bottom and follow that path, that orange path, up to the top. 3 skiers went that way, right? Now the other path that I'll highlight in red, whoops, red. I'll highlight this one in red. This path, okay, where the electrons had gone this way, well, we see that only 1 amp went that way, okay? So if 3 amps went to the left and 1 amp went to the right, how many amps flowed into this junction right here? Well, it must be 3 plus 1 equals 4 amps. So this value here is 4 amps flowing in. Now, actually, that makes perfect sense because these guys at the top, I'll go back to my rainbow color, these guys at the top of my picture, that's 4 amps up there. We know 4 amps are flowing back to the battery. Well, that means that 4 amps must flow out of the battery. Like 4 guys get on the chairlift, 4 guys must get off. And it's got to be 4 amps here that split up at the junction to 3 and 1. Then they get back together to make 4 again, and then they go back to the battery. Okay, and then they do the whole process over again. So there you have it. I mean, that's how you do the current law. Now let's check this one off, and let's do number 2, find the missing voltages. Now remember the single path rule, okay? Because there's more than one path here, okay, we have to be a little bit careful. So what I'm going to do is I'm going to color one path in red and the other path in highlight color, okay? So watch. Right now I see, I'm going to erase this yellow here because it gets a bit confusing. Right now I see that this voltage here is given and this voltage here is given, but I have 2 missing voltages, this one and that one. How do I find out what those voltages are? Oh, and by the way, very important, I also know the voltage in the battery is 18. Okay, so remember, think of it like a ski hill. The chairlift takes you up 18 meters, let's say. Okay, and you have to drop 18 before you come back to the chairlift. So let me explain. Let's say we take this yellow path. So follow my yellow path. I'm going to go through that resistor. I get to the fork in the road and I am going to turn right. I'm going to go up this way, back to the junction and out and back to the power supply. So what I just highlighted in yellow is one single path. Okay, it's one single path. Now, if I look at that path, I've chosen my path carefully so that only one thing is missing. Okay, if I look at this path, first I have this unknown amount that I dropped here. Okay, then I continue along the path, I turn right, I go up through the first resistor, and I've dropped 3 volts here. I keep going, I go back to this path at the top, and I drop 6 volts there, and then I'm back at the battery. Now, how much voltage do I know I've dropped? Well, 3 plus 6 is 9, but I have 18 volts, so that means this missing guy down here must be the rest of it. Okay, I have to spend all the money. So 18 minus 9 is 9 volts. So this V4, I'll write it right here, V4 would have to equal 18 minus 9 equals 9 volts. So I found one of my missing voltages. All right, so that's one missing voltage. Can I find the other missing voltage? Well, let's see. What I'm going to do is I'm going to erase some of these lines. Okay, so I erase my path. Now I'm going to draw another yellow path, but this time I'm going to make a different choice about the direction I take. So I go here, I go through this resistor. Now, instead of turning right at the junction, I'm going to turn left and take the other path. Okay, and then I come up here, and then I'm back at the battery again. So now taking that second path, can I find the missing voltage, which is now this voltage right here? Can I find the missing value? And the answer is for sure, because I already know that V4 is 9 volts. Okay, so if I follow the path, I first drop 9 volts there, okay? Then I continue on here, an unknown voltage here. Then I continue along the path and drop 6 volts up here. Well, 9 plus 6 is 15, but I have a total of 18 volts. So therefore this one has to be, V2 has to equal 18 minus 15, which is 3 volts. So it's 3 volts, that's what goes in here. Now, is it a coincidence that the other parallel path also had 3 volts that was given on that side? That's not a coincidence. After all, if you're skiing on a hill and you go left and I go right, and we both meet up later on down the path, we'll have to have dropped the same amount of vertical height to get to the same point on the path. Here where the junction is, right there. That's where we meet up again. And so we'd have to drop the same amount to be at the same spot on the hill at that point, right? So it's not a coincidence, it does make sense. So there you go, that's about as hard as these questions get. Now before I show you the worksheet, because that's really the end of the lesson, but before we show you the worksheet, I wanted to show you that, you know, there is a practical application to this. All right, so here we have a parallel circuit. Now I've left everything disconnected on purpose. So what I'd like to do is just make some connections for you. So I'm going to connect this wire here. I'm going to connect this wire there. Okay, like that. So I'm going to raise this up a little here. Okay, so right now I only have one path that's connected. Okay, and it's working. I'm getting 1.07 amps. Now along any single path, the current has to be the same everywhere. And so I get 1.07 amps all the way through. Now if I take a second wire and attach my second path, okay, now what's happening is my current values, you'll notice, have changed. This is because now I have more than one path. Okay, so let's see if you can understand what's happening here. I have, you know what, I'm going to change the voltage of my power supply. Here, let's make it easy. There we go. Okay, so if you look at this, right here, I have 3 amps. okay? Now 3 amps is, that's how many amps are getting off the chairlift. Remember, the battery is my lift. It's giving me potential, pushing the electrons, right? Okay, now some people went that way, okay? Some will continue along this way and then travel down that wire. And if you look at it, it's not equally divided. So this is our junction right here. How many electrons are flowing into the junction? Well, how many amps? 3 amps flowing in. And I have 1 amp going through the resistor, 2 amps going through the light bulb for a total of 3 amps. And you see how the law works, right? Now, if I were to measure voltages, okay, I'm just going to erase my lines that I drew. If I were to measure voltages here, okay, my battery voltage is set to 20 volts. Now, if I take the first path, there's really only one possible drop. So if I take this path, okay, I had $20 to spend, and I'm only going to go through the store right here, that store only, okay? So how much am I going to spend there? Well, I have to spend everything, right? And that's exactly what you'll notice. You'll see here in the meter reading is 20 volts. So I've spent all of my energy at the one store. Now, what about if I go to the light bulb? Well, if we go to the light bulb, I'll find that I have spent $20 there also. Now, how is this possible? Okay. Well, remember that the electron, if you're an electron, you didn't visit both stores. You only went to one. You have to pick which path you're going to go down. Now, if you prefer the ski hill analogy, both of those paths lead to the bottom of the hill. Okay. So the light bulb is one run down the hill, and the resistor is the other run. You're going to have to drop everything by the time you get to the bottom. So you're going to have to drop all 20 meters, okay, that the chairlift gave you. And that's exactly what you do, okay? So this is the more difficult path, which is why the electrons are moving more slowly through it. And that's why it gets less current. So this path has higher resistance, right? This would have the higher R value, okay? So that's not surprising that we see less current going there. They don't have to have an equal amount of current being split up between them. All right, so that's how the current law works. Now I'm going to break these connections. I'm going to break this one too. Now I'm going to construct a series circuit. Let's get rid of some of this wire. I'll break this connection as well. Let's delete that wire. Okay, I'm going to move my light bulb over here. I'm going to connect it with the wire. Then I'm going to put my resistor in here. Actually, I'll delete this wire and just connect my resistor directly. And then I'm going to connect my missing wire here like this. Okay, this is now a series circuit. And you can see how it works with the electricity following a single path. There's only a single path, right? Now, notice that the current is the same number, no matter where you measure it. That's because the electrons are moving through the circuit at a uniform rate. You can see they only have one path, so they can't split up. Okay, so they take the one single path and they sort of migrate around the circle, drifting through. This still being the chairlift here that brings them to the top. But now they don't have a choice about what run they're taking because there's only one way to get to the bottom, and that is through the light bulb and the resistor. Okay, now if we look at the voltages, the battery is still set at 20 volts, okay? So now I'm gonna check my light bulb. What's the voltage across my light bulb? Well, the light bulb checks in at 6.67 volts. Okay, so definitely not the whole thing. Whereas my resistor checks out to 13.33 volts. Now, if I add those two numbers together, okay, the light bulb was 6.67 volts, and this one is 3.33 volts. If you add them together, you get 20 volts, which was this was 20 volts down here. And so what you can see is that the voltages add up, okay, to give you the voltage in the battery. And that's what they're supposed to do. So there's the voltage law. Okay, so everything works the way I've been describing it to you. And it's pretty straightforward. Let's get back to OneNote. That's the whole lesson for today. Okay, I have a little assignment for you. So in this assignment, find all the missing voltages, okay, and find all the missing currents. Do the same thing down here, okay, in the second circuit. And then if you read this question here, it says, whoops, it says find the power loads of the loads in question one. That's all the resistors in question one. You can use power in the first resistor would equal V1 times I1. So if you can find the missing voltages, okay, you can find the power outputs. Now, if you don't want to use VI, you can use I squared R, or you can use V squared over R. But just make sure you use the voltage that and resistance that goes with that device, that particular device in the circuit. Okay, and that's it. Now, this question here, question 3, you could have answered yesterday. So please go ahead and do that. That's using power, voltage, and current and Ohm's law and stuff. So go ahead and do that based on what we learned already. Now here you have to draw a circuit diagram. So please go ahead and do that, okay? And do it in series and in parallel. And then for question 5 and 6, okay, I want to see if you can, these are a bit trickier, okay? But give these two a try. See if you can figure it out, okay? Yeah, that's it, guys. Please don't do any other homework other than this sheet today, okay? So what we just did, in case you're wondering, in the homework outline, I have changed the order slightly, okay? So we just did this lesson here. I don't want you to do this. There's another worksheet. So technically this is lesson 12, but I have switched the order of these two. We did 13 first, and then we just did 12 today. Any questions? No? Perfect. You guys are geniuses. That's awesome. Okay. So that will take us to the end of the lesson today. Have a good day, guys. I hope you enjoyed that. I mean, it was very exciting. I know you enjoyed it. And we'll talk to you soon.